Hello, this is Tracy, and we are going to test a hypothesis about a population proportion. And we're going to use p-values, not the rejection region and test statistic. You are welcome to do that, and that is covered in the textbook and in the Hawks videos. So in this section, we're first of all going to determine if we can even use the methods we learn in this section. We are going to test a hypothesis or a claim about a population proportion using p-values, and then interpret the conclusion of a hypothesis test in the words of the problem. Our Hawks Online homework is 11.4b, the p-value method. All right, so in order to use the methods we're going to learn in this section, well, the methods, in order to use the calculator function that I'm going to show you in this section, we need to make sure that some conditions are met in our problem. We need to make sure we get our data from a random sample of size n. We need to make sure we have a binomial random variable. The number of trials must be fixed. Each trial has to have two possible outcomes, a success or a failure. And the n trials that we have should be independent, and the probability of success should be the same on every trial. The expected number of successes and failures should both be at least 10. So we take the size of our sample, n, times the true proportion of successes, multiply those together. That should be bigger than or equal to 10. We take the sample size and multiply it by the proportion of failures. Again, that should be greater than or equal to 10. So here's our problem, and we're going to make sure this problem fits into the type we're doing in this section, and then we're actually going to do it. Over the past few decades, public health officials have examined the link between weight concerns and teen girls smoking. Researchers surveyed a group of 273 randomly selected teen girls living in Massachusetts between 12 and 15 years old. After 4 years, the girls were surveyed again. 63 said they smoked to stay thin. Is there good evidence that less than 30% of the teen girls smoke to stay thin? So we want to make sure, we want to figure out what it is we're trying to do. Now, because we are in the section about testing a hypothesis about a population proportion, you know what's coming. But on a test in the real world, you may not have it quite so obvious where you're told, here's the type of problem, now go do it. You're going to be given a problem or a situation, and you need to figure out what to do. So here we're going to look at that last sentence. Is there good evidence? And that good evidence question right there tells you you're going to be conducting a hypothesis test. Is there good evidence that less than 30% of the teen girls smoke to stay thin? That 30% right there, you are being asked about a proportion. Is it true that less than 30% of the teen girls smoke to stay thin? We are looking at the proportion of successes where success, and again, we don't mean success is a good thing, we just mean success is the thing we're studying. Success is smoking to stay thin. And again, I shouldn't have said, is it true? We never speak of truth in the problems that we do, or even in the real world. We support or fail to support. We reject or fail to reject. We do not determine truth. No amount of statistics can do that. So we are conducting a hypothesis test about a population proportion. We are asking if there is evidence to support the claim that some percentage of a population fits, some percentage of a population has a certain characteristic. Now we need to make sure that we can actually use the calculator button I'm going to show you. If not, we would pawn it off on somebody else who has done more statistical study, and they would use more advanced research or more advanced methods. So, did we get our data from a random sample of size n? Well, in our problem, it tells us researchers surveyed a group of 273 randomly selected. That phrase right there, randomly selected. Yes, we have a random sample, and they give us a number, 273, size n. If we're not told that in the problems in the homework or on the test, we have to assume we have a random sample. In the real world, if you were conducting the study yourself, you'd make sure that you had a random sample. And if somebody else did it, you would want to make sure that their methods are valid, or else no amount of statistical analysis is going to have any meaning whatsoever. Do we have a binomial random variable? Well, do we have a fixed number of trials? Yes, 273 teen girls are selected. Each trial has two possible outcomes, success and failure. Well, again, success is smoking to stay thin. Failure is not smoking to stay thin. Two possible outcomes. The end trials are independent and the probability of success is the same on every trial. We don't know that in this problem. We have to assume it, otherwise we can't do anything. And again, in the real world, make sure you do your study well, or check that the researchers who gathered the samples did their study well. We can check that the expected number of successes and failures are both at least 10. So we have 273 teenage girls in our sample, and we expect 30% of them to smoke to stay thin. So we take that 30%, 0.3, and multiply it by our sample size, and the number we get, 81.9, is definitely bigger than 10. And the expected number of failures is even bigger because the probability of failure, 70%, is even higher than the probability of success. So here are the steps of the hypothesis test. I can't remember if this is out of the homework or the textbook, but this is kind of what you're walked through in our textbook, online learning system, all that good stuff. We'll walk through the steps once, but then you may also get problems where you just get the problem and you need to know what steps to go through. And you're probably noticing that these steps are familiar from different type of hypothesis tests to another. You pretty much do the same thing. Determine your hypotheses, determine what type of test, what button to hit on the calculator. Is it one-tailed or two-tailed? And you need to know that so that you can know how to input the data once you pick the correct calculator button. Determine your level of significance, find your p-value and test statistic, make your decision to reject or fail to reject, and then interpret. So here are hypotheses. Your null hypothesis is that the proportion is equal to some value, and that value comes from common wisdom, previous results, status quo, assumed results, all that good stuff. In our case, the problem we're given claims that 30% of teenage girls smoke to stay thin. That's the kind of what's already been found by somebody else. The alternative hypothesis is what we are saying that could be different. This is the alternative claim we're making, and we are testing the claim that less than 30% of teen girls smoke to stay thin. So that's our alternative hypothesis. And here we go. Our null hypothesis is that the true proportion of girls who smoke to stay thin, teenage girls who smoke to stay thin, is 30% or 0.3. And we want to test the claim that the true proportion is less than that 30%. P is less than 0.3. What type of test are we conducting? We know that this is a hypothesis test about a population proportion. And so we are going to go to our calculator in our stat tests, and we are going to choose the option that tests a claim about a population proportion, a single population, teenage girls. So we go to stats, tests, and number 5 on most of your calculators will be the one proportion Z test. One proportion because we're dealing with a single population and we are making a test about the population proportion, and a Z test because we are using a normal distribution to approximate the binomial distribution we get from looking at successes and failures. So is this a one-tailed or a two-tailed test? That we get by looking at our alternative hypothesis. If our alternative hypothesis is that the proportion is less than the value in the null hypothesis, we have a one-tailed test. If the alternative hypothesis is that the proportion is greater than the value in the null hypothesis, we also have a one-tailed test. The only time we have a two-tailed test is if our alternative hypothesis is that our true proportion is different than, is not the same as the null hypothesis. That's when we'd have a two-tailed test, because then we care about whether the proportion is either too small or too big. All we care about is that it's different. We're not looking in one particular direction. Now, we need to identify or choose alpha, the level of significance for the hypothesis test. I think our book or the homework puts this later in the process, but you should have your alpha in mind before you find a p-value. Alpha tells you how unusual your results need to be in order for us to reject the null hypothesis. Remember, the p-value tells us how likely our results are given that the null hypothesis is true. Alpha is, well, how unlikely does that probability need to be before we say, we don't think we believe that null hypothesis, we're going to reject it. If you don't choose alpha in advance, then you might be tempted to get a p-value and say, well, what should alpha be to make my results statistically significant? And that's not exactly ethical, so get your alpha in mind first. If alpha is not given to you, you would choose it. And you would choose it based on how confident, how certain you want to be. If you want to be 95% certain of your results, alpha would be the decimal of what's left out of 100%. 100% minus 95% is 5%. Alpha would be 0.05. If you want to be more certain about your results, you really want to make sure that these results are unusual before you reject the null hypothesis. You might want to be 99% certain. Alpha would be 1% as a decimal, 0.01. If you don't need to be quite so sure, excuse me, you could be 90% certain, then your alpha would be 10% as a decimal, 0.1. Sometimes you want to be really certain, and then you would have something like 99.5%. Your alpha is really tiny, 0.005. 99.9%. Oh, alpha's even tinier, 0.001. But for us, let's just go with alpha equals 5%, 0.05. We want to be 95% certain before we say, no, our results are crazy. Here is how to
All right, let's go ahead and conduct a hypothesis test for a population proportion. So again, for hypothesis testing, just like with confidence intervals, we go to our favorite button in the stats class, stat. Again, just like with confidence intervals or any other hypothesis test, we arrow over to tests. In this case, we are conducting a hypothesis test about a population proportion. We are testing a claim about what proportion or what percentage of a population has a particular characteristic. So for this, we are going to use the, the one proportion z-test. And it's a z-test because we are using a normal distribution to approximate the binomial distribution you get anytime you are dealing with a proportion. What percentage of successes do you have? So, number 5. And we just need to go ahead and fill in the pieces. In this problem, the null hypothesis is the claim that the population proportion is 30%. So P0 or P0, that thing right here, first thing, is what we claim in the null hypothesis is the population proportion. 30%, 30 divided by 100 is 0.3. All right, X is the number of successes, and in this problem, we have 63 girls who said they smoked to stay thin. Oh, depressing, isn't it? All right. And the number of trials. We looked at 273 randomly selected, teen girls living in Massachusetts. Now here, we are going to put the symbol that we use in our alternative hypothesis. We are testing the claim that the true proportion, the true percentage as a decimal point, is less than 30%. That's what we're given in the problem. That's what we used for our alternative hypothesis. Arrow over and then enter so that we are on, oh, that's not less than. Try that again. Less than. Okay, that's what we want to be. Our alternative hypothesis is that the true population proportion is less than 30%, is less than this P naught we claim in the null hypothesis. Now arrow down, arrow over to draw. Go ahead and draw it. And here are the results we will talk about on the next screen.
And here are the results we get. So this sketch shows us how likely our results are. The p-value does too, but the sketch shows us. We can see that little tiny bit of shading there in the left tail. Not a lot of shading. So we would look at our p-value and see how likely is it to get our results if the null hypothesis is true. Not a lot of shading, probably a low probability, and our p-value reinforces that, 0.0063. That is a small percentage. That is a small probability. That's less than 1%. Remember, 0.01 is 1%. This is smaller than that. And our test statistic, that z-value, also tells us our results are awfully unlikely. Our results are about 2.5 standard deviations below the mean of the sampling distribution of the proportion. The sampling distribution of the proportion has the null hypothesis proportion at the peak, 0.3, and then we expect most samples to have a proportion that clusters around that 30% if the true proportion is 30%, and only the rare freaky samples out on the tails. So that that Z statistic, test statistic says our results are 2.5 standard deviations away from what we expect if the null hypothesis is true. Either we got a freaky sample or the null hypothesis is not true. So again, here's what our p-value is saying. P-value is 0.0063. Tells us the probability of getting our results. 63 teenage girls who smoke to stay thin out of 273, which is a proportion of 0.231 or about 23.1%. The probability of getting 23.1% or lower if our true proportion is 30% is only 0.0063. So that is unusual. We just want to make sure it's unusual enough, and alpha tells us that. So again, our test statistic rounded to 2 decimal places like your homework likes. Remember that negative 2.496, 6 comes after the 49, so we would round that up, but 9 rounds up to 10, 49 rounds up to 50. Negative 2.50 standard deviations below the mean of the sampling distribution of the proportions if the true proportion is 30%. So that's pretty far away, quite a bit below. Now we want to know, does this cause us to reject or fail to reject the null hypothesis? Again, we had a low probability of getting our results, 0.0063. Is that low enough? Our alpha is how unusual our results need to be in order to throw out the null hypothesis, in order to reject it. If our p-value is less than alpha, we reject the null hypothesis. If our p-value is greater than alpha, then our results are not unusual enough to reject the null hypothesis. We expect to get stuff like that every now and then. Our p-value of 0.0063 is less than our alpha of 0.05. We reject the null hypothesis. Our result, a proportion of 0.231, is low enough if the true proportion is 0.3 that it's just too unlikely. This is freakishly unusual. We don't think the null hypothesis is correct. We reject it. And what does that mean in the words of the problem? We reject the null hypothesis. We reject the claim that the true proportion of teenage girls who smoke to stay thin is 30%. We were looking at the claim that the true proportion is lower than that. And with the p-value we have, we reject the null hypothesis and we support the alternative hypothesis. Our data support the claim that the proportion of teenage girls who smoke to stay thin is lower than 30% at a significance level of 0.05. Our p-value was 0.0063. It's nice to include a significance level and a p-value to show how much our data support the claim. If we had a significance level of 0.1 or 0.15 and our p-value was something like 0.13, that wouldn't be nearly as impressive as the p-value we got. And then in the next section, you will look at the difference between statistical significance, what we have here, and practical significance. Is the difference we got big enough to have any meaning in the real world? All right, that was a hypothesis test for a claim about a population proportion, how to use your calculator, how to interpret. As always, let me know if you have any questions.